In this video, we will connect the movement state events we wrote in the last video with our world render component, so that we can update the rendering of the citizens to match the changes being made by the movement state. The first thing we'll do is subscribe to the render update events on the citizen class. We will use the setup events method to subscribe to these events, and we will define two private methods to respond to these events. They will be named onUpdateCitizenRenderDirection and onUpdateCitizenRenderPosition. Remember, they both need to match the signature that is expected by the event handlers in the citizen class. Now that we have the methods defined, let's subscribe them to the event handlers in Setup Events. Let's also make sure to unsubscribe from these events in the onDisable method. We can also remove the start and update Unity callback methods because they will not be used in this component. The method that updates the render direction is actually quite simple. To update the direction, we simply play the correct idle animation. Remember, our play animation method accounts for the citizen's current direction when deciding which animation clip to play. So simply calling this method on the citizen with the idle animation type will be enough to update their render direction. We get the citizen from the event args as usual, and we pass the idle animation type for the second argument. The method that will update the render position is quite a bit more complicated. We are going to define a coroutine in order to make it look like the citizen smoothly moves between two tiles. In our simulation, the citizen actually instantly moves to the next tile and then simply waits for their cooldown to complete before attempting to move again. There is no reason for our simulation to keep track of all the positions in between the tiles. It would complicate the simulation for no reason at all. But for rendering purposes, we do want to make it look like the sprite is actually moving from one tile to the next. To handle this movement, we will start a coroutine. A coroutine is basically a method that you can run over the course of many frames, instead of running it all at once and blocking the rest of the application from running. It is possible to use the yield keyword within a coroutine to hand control back to the application. Then, on the next frame, the method will be allowed to pick up where it last yielded, and it will continue until it either finishes or reaches another yield statement. This will be the perfect mechanism for handling the smooth movement of our citizens between tiles. Each citizen will be assigned a coroutine whenever they move between tiles, and then they will move a small amount each frame until they reach their destination, pausing each frame to yield back to the application. Let's get started by defining the coroutine method. We will call this method moveCitizen. Every coroutine needs to return an IEnumerator. This return value is how Unity keeps track of the method execution between frames. Our method will take the citizen we are going to move as its only argument. We will need to import the system.collections namespace in order to get access to the IEnumerator type. Every monobehavior component has access to a start coroutine method that we can use to begin executing a coroutine. Let's call this method in onUpdateCitizenRenderPosition. Notice that this method takes an IEnumerator as its only argument. So to begin the coroutine, we call our method, which will then return an IEnumerator reference that will be passed to the start coroutine method. Now we can begin building the coroutine method. We want to slowly change the citizen's render position over the course of its cooldown, so that it arrives at the next tile exactly when its cooldown has ended. To do this, we will set up a timer within our coroutine method. To calculate the length this timer should run, we are going to multiply the citizen's cooldown by the length of one tick. This is stored in our simulation info class inside the variable called tick duration. A citizen's cooldown is the number of ticks that it must wait until it can move again. So for us to calculate the total time of their cooldown, we will multiply the cooldown by the tick duration. We will now get the render data that is connected to the citizen we are trying to move and store it in a local variable. Even though we have already updated the citizen's position in our wander state, we can still access its previous location because it is still being rendered at that position. Remember, the rendering of our citizens is not connected to the simulation directly, so we can store the start position of our citizen in a local variable by simply retrieving it from the world game object transform in the render data. This position still points to the previous tile because the rendering has not been updated yet. Now we want to calculate the end position of our citizen's movement. We will have to calculate this position because all we currently have is the citizen's position in the simulation on the 2D map. This will be the exact same calculation we did when we created the render data for the citizen. We can use the grid to world method again and then make sure to set the Z value to avoid the flickering we get with Z fighting. We'll call grid to world on the citizen's current position and then we'll calculate the Z value using the entity spacing variable that is stored in our render settings scriptable object. We're about to begin moving the citizen, so the first thing we'll do is call the play animation method to update the citizen to its walk animation. Now we will introduce a while loop that will allow us to move the citizen a small amount each iteration, and then we will yield control back to the application at the end of each loop. Our while loop will continue running until our timer variable hits the cooldown duration. So the first thing we need to do each iteration is update the timer. We will add the delta time since the last frame. Now we are going to calculate the new position to move the citizen to by using the linear interpolation method in the vector3 class. Remember, this method takes a starting position, an ending position, and a value between 0 and 1. When a value of 0 is provided, the method will return the start position. When a value of 1 is provided, it will return the end position. And when a value of 0.5 is provided, it will return the position halfway between the two vectors on a straight line. So we need to calculate a number between 0 and 1 each frame that represents how far along the journey our citizen should be rendered. It turns out that dividing our timer value by the duration value is exactly what we want here. When the timer is at 0, the citizen will be rendered at the start position. And when the timer equals the duration, the citizen will be rendered at the end position, because the timer divided by duration will be 1 at that point. Now all we have to do is update the transform position of the render data so that we can actually see the citizen at its new position. We will access the world game object for the citizen and then set its transform position to the new position variable. Now we can yield control back to the application until the next frame. We will do this by yielding return null. This will yield for one single frame. Then the execution will be returned to the point right after this return statement on the next frame. Then our loop will run again. To complete our coroutine, we will set the render data position to the end position exactly. Notice our while loop will end when the timer equals the duration, so we still need to move the citizen the last step. This will also ensure they always end exactly where we want them to end. Now let's take a look at the application to see our new movement states in action. Right now, the citizens are all set to the idle state. We can see they each wait for their cooldown to complete, then choose a new direction to face. This is exactly what we were expecting to see for the idle state. Now let's go back and set them all to the wander state and check to make sure it is also working correctly. We will go to the citizen class and change the state they all begin with to the wander state. Now let's run the application again and take a look. As you can see, they all begin smoothly wandering around the map. Remember, the citizens are actually moving instantly from one tile to the next. In the simulation, they simply update their position automatically and then wait for their cooldown to complete before attempting to move again. But the rendering component begins a coroutine in response to the event that is fired when they change position, and this coroutine smoothly moves their sprite's render position between the two tiles. Our timer calculation ensures that they move between the tiles in exactly the right amount of time. This creates the illusion of smooth movement, even though the actual simulated positions are being updated discretely. Let's go back and set the citizens to the idle state for now. In the next video, we are going to extend our map system to make it easier to build up our map with more complicated structures for the citizens to wander around.